Hello, good morning. So today we are going to see a C++ program on the operations of binary search tree, and these operations are going to be creation of binary search tree and display of binary search tree by pre-order traversal, which is a recursive function, and then we'll use a non-recursive function of pre-order, and that is for finding the height of binary search tree. So this is what we are going to see today. So we'll start with the C++ program now. So I will use a compiler here, a C++ compiler, and then on that compiler, we'll start with the program. So this is the compiler which we'll use. So I will share it. Okay, so this is the compiler which we are going to use, and in this compiler you can see this is the multi-line comment. In multi-line comment I have mentioned a C++ program for creation of binary search tree, display of binary search tree using pre-order. So I will write here, it's a pre-order traversal, so pre-order, and then we'll find the height of binary search tree by traversing the tree by pre-order. So this pre-order, which is used for display in the second operation, is a recursive function. So we'll mention here it's a recursive function, and in the pre-order traversal, which we use for finding the height of binary search tree, so that will be non-recursive pre-order. So that will be used here. So we can say here we'll use the pre-order traversal in the third operation, and that will be a non-recursive pre-order. So, so this is non-recursive using a non-recursive pre-order. Okay, so as it is a binary search tree, so what we need initially, the node structure, and before a node structure we need some header files from C++. So we'll first take the C++ file, header files. So what are the header files we required? So these are the header files which we required. So here we have those header files. So see, so these are the header files which we required: IOStream, namespace, and stack. So why we have taken this stack as a header file? Because we are going to use a non-recursive pre-order. So in that non-recursive pre-order, we are going to use a stack for keeping the track of the nodes for backtracking. So for that, this stack header file is used. So we are going to use this ready-made stack. So we are going to call the functions which are necessary, like push, pop, etc. As well as we can use the top pointer. So after this, we'll go ahead and then we'll create the node structure for binary search tree. So this is the node structure for binary search tree. So you can see here we have a class BST node, and in that BST node we have a public section where we have the data members of that node structure is integer data. We have a level, so we are going to store data along with the level of the node. So level of the node will be stored inside that node structure, and then we'll have two pointers as it is a binary search tree. So we'll have a left and right pointers, and then at the end of the class we are declaring a root. Okay, so this is the class for BST node. Now we'll write one more class for binary search tree operations. So we have three operations: create binary search tree, display binary search tree, and find height of the binary search tree. So these three operations will be mentioned here in the class BST operation. So we have this class BST operation, and in this we are mentioning initially a BST node, pointer node, as a data member, as we are going to create nodes of type class BST node having data, level, left and right pointers. So that will act as a data member here. And in the public section, we have these functions: creation, show pre-order, and find height. So for creation, we are accepting root, which is initially null, and then we return the root from the function. Hence, its return type is BST node pointer. In the show pre-order, the return type is void, but it has a parameter which is root. Then, in case of find height, we return the height of the tree from the function. That is why its return type is integer, and it has two parameters. One is root, from where we start the traversal to find the height of tree, and then second is a max integer max variable which will store the height of tree. Okay, so we'll go ahead now for the functions. So now we'll first define the functions outside the class using that syntax, return type, class name, scope resolution, function name, and parameters. So here we have the first function for our class. So this is our first function. So see, BST node pointer, BST operation is a class name, scope resolution, function name. This is our function name, and these are the parameters. Okay, so this is the syntax which is required to define a function, member function outside the class. Now these are the variables, pointers required for new node and parent node, and these are the integer variables required for loop, number of nodes, level of the node, and flag. So after that, we'll ask user how many nodes to create. So what user will do, user will enter the number of nodes to create, and then we'll start a loop to create those number of nodes. So this is the for loop which we are going to create. So this we have here. So see, initially we have asked user how many nodes to create. So we'll start a loop for those number of nodes. And then we create a node here by allocating memory dynamically. Then we ask for the data for the new node. Then we initialize the left and right pointers of the new node to null. And then initially the level of that new node is 0. Initially, the levels of all the new nodes are 0, and then we assign those levels when we attach those nodes into the BST. So initially, if the root is null, what we do? We assign root equal to new node. So this is the first node which is attached inside the binary search tree. So we have created first node and we have attached it as a root. Now we are going to create number of nodes. So those other nodes will be going to attached inside a binary search tree by else part. So in the if part, we have created the root node. Now in the else part, what we will do? We will attach the other nodes. So these other nodes will be attached here in the else part. So what will be the else part? So this will be the else part. See, if is over, now else. What we are doing in else? We are assigning parent equal to root. So we'll store the address of root inside a parent pointer. We'll initialize level equal to 0, flag equal to 0. Okay, so flag is the variable which is initially 0, and it will be 1 once that new node is attached inside a binary search tree. Okay, so when the new node is successfully connected inside a binary search tree, it is successfully added, then it becomes 1. So while this flag is not equal to 1, until that new node is not added, what we do? We search for its parent node. So until once we get the parent, we attach it. So for binary search tree, we have a logic of whether new node's data is smaller than parent's data or greater than parent's data. So if it is a smaller than parent data, that new nodes becomes the part of left subtree. Otherwise, it becomes the part of right subtree. So here we are comparing if the new node's data is less than or equal to parent arrow data. So what we do, we check for whether parent's left is null. So if it is less, new node's data is smaller than parent's data. So we check whether parent's left is null. If yes, we increment level. So initially level variable was 0, it will become 1. And then new node arrow level will be assigned to level. So now new nodes level will be assigned here. So it will be like 1. And then we attach that new node as the left child of new node. So see, we are assigning the new node to parent's left as the new node was smaller than parent data. And then we make the flag 1. So once we attach the new node, we make the flag 1. Similarly, if the parent's left is not equal to null, so what we do? That means we have to shift the parent to its left. So in the else part, we do this, we shift parent to parent's left and we increment level. Because whenever we shift parent to the lower level, the level is incremented. And then we assign this level to the new node when it is going to be attached inside a binary search tree. So this is how it will be done for if the new node's data is smaller than parent arrow data. Now what if the new node's data is greater than parent arrow data? So for that we have this else. So in the else part, if the new node's data is greater than parent arrow data, so we'll do the similar process for parent arrow right. So we check if the parent's right is null. If yes, we increment level, we assign that level to new node, and then we say parent arrow right equal to new node. So this is how we attach new node, and then what we say flag equal to 1. So here the flag becomes 1 because the node is successfully inserted. Now else, otherwise, what otherwise? If the parent's right is not equal to null, we shift parent to its right. So how we shift parent to its right? By parent equal to parent arrow right, and then we'll increment level. So this is how the level is incremented because we are going down into the tree. So level is incremented. Then we close else here. We close this outer else, this else here, and then we close while. So this while says until the flag is not equal to 1. So when we attach, we make flag 1. So we come out of this while loop, and then after while we close this else, and this else will be closed here, and then we close the for loop. So this for loop will come out of this for loop when all the nodes are created and added successfully into the binary search tree. So as the binary search tree is created having a root node as the first node, so we return root from here, from the function, and that is why the return type of the function was BST node pointer. So this was the return type. Okay, now we'll see the definition of second function, and that second function will be the pre-order, which is a recursive function. So what is that recursive function of pre-order? So here is the code for that recursive function. So this is the recursive function pre-order. So void BST operation, show pre-order, root is a parameter. So if root is not equal to null, what we say will display the root arrow data as well as will display the root arrow level. So when we access the data of the node, we display data as well as its level in a bracket. So after that we travel to its left subtree and then to its right subtree. So this is pre-order, data left, right. So this is the function for pre-order. Now we'll see the function for binary search tree height. So we are going to find height of a binary search tree, and that is by using a non-recursive function of pre-order. So we'll have that non-recursive function here. So this is the definition for finding height. So see, we have this integer is a return type. We are going to return the height of the tree. This is the class name. Then we have scope resolution operator. then function name, and then these are the parameters, a root and the max variable. So initially max is 0, and then we check whether max is smaller than the node arrow level. So the level of the node will be used to check the height of the tree. So when we catch the highest level from a node, so that is the height of the tree. So see, initially in the class, we are declaring a stack. So this is the ready-made stack, which we are using from that header file stack, hash include stack. So here we need to pass the type of stack. So this type of stack indicates what value the stack is going to store. So stack is going to store the addresses of BST node. So that is why its type is BST node pointer, and this is the object S. So we'll use the stack operations like s dot push. So object dot function name, and then we pass the parameter that is root here. So what we want to push into the stack, address of the node. What we want to pop from the stack, address of a node. So this is how we do. Now after this, we will start non-recursive pre-order, and this non-recursive pre-order for traversal and finding the height of the tree will be this. So see, this is our function find height. This is our stack created here, and initially we pushed root inside the stack. So initially the root is pushed inside stack, and then while stack is not empty, what we are going to do, we are going to do the traversal. Okay, so this traversal includes, we have to take address from the top of the stack, and that address is stored into temp. So initially we pushed root. So what is there on top of the stack? The address of root. So that address of root will come inside temp. So after this, I will check if the value in the max variable, which is initially 0, is smaller than the root arrow data or temp arrow data. If it is smaller, then we assign that greater value to max by this statement, max equal to temp arrow level. So here you can say, instead of saying whether the max is smaller than temp arrow data, we should say whether max is smaller than temp arrow level. So we should compare max with the level of the node. So this temp is the node. So if the max is smaller than temp arrow level, then we assign max equal to temp arrow level. So this is the logic to catch the maximum level of the node, and that maximum level will be height of the tree. So after this, we'll do the access to next nodes in the tree by doing this s.pop. So s.pop means remove the node which is there on top of the stack, and then add its right child into the stack. So push the temp arrow right into the stack if it is not null, and then push its left child. So why initially right and then left? Because when we push right first and then left, so the pop is left first. So it is pre-order. So what we want? Left first. That is why we are pushing right and then left. As stack is last in first out, so left will come out first. And then we'll do what? Take the address from stack top s.top, and then check whether max is smaller than temp arrow level. So whether the max is having the smaller value than the node's level. If yes, then max equal to the level of that node. And this is how the max will ultimately, eventually catches the highest value or highest level of the node, which is deepest in the tree. So this is how we'll get the height of the tree, and then we return this max. See, after this while loop, see, we return max from the function. So this max will be returned from the function, and then we use that max to display the height. So we have a main function now where we are calling all these above functions. So now I will show you the main function here. So this is the main function. See, now in this main function, we have initially the title of the program, binary search tree rather. So we have this binary search tree here. After this, we have initialized root equal to null. Then we have created an object of the class, and then we'll do the first operation here, and that first operation is creation of binary tree. So see, I'm calling the create BST by using object. I have passed root, which is null, and then I'm catching the root, which is returned from the function. So this is how creation will be done for number of nodes in the binary search tree. Then we'll do display. So I'm calling this pre-order for display function. So it will be a recursive pre-order, and then I'm using non-recursive pre-order using stack for finding height of the tree. So this is for finding height. So initially max is 0. I'm passing this max along with the root. See, I'm passing max along with the root to the function, and then this function will return the max, which is cached here. So initially max is 0, which is passed, and that function return finally the max having the level of the deepest node, and that level of deepest node is nothing but height of our tree. So then we'll display here the height of the tree. Okay, and then return 0 from main function. I hope you have understood this code. So let us run the program. So see, we have run the program. We got here binary search tree, create binary tree. So it is the first function called for creation. So I will say how many nodes you want to create. So I say I want to create 8 nodes. So these 8 nodes are, initially my first value root will be 10. Then onto the roots left, I will enter 5. Then to the 5's left, I have 2. Then to the 5's right, I will have 8. Okay, so there is some problem. Okay, so after 8, I'll enter onto the 10's right, roots right, and that is 15. Then onto the 15's left, I can enter something, and that is there is some problem in the running. Okay, let us run again. So let us enter initially a smaller number of nodes. So suppose I'm entering three nodes. One is root, which is 10. Then we have 5, which is the left child. And then we have suppose 20, which is the right child of 10. Now, see, this is how we'll get the display. So 10 is the root on level 0. 5 is the left of 10. So it is on level 1. And 20 is the right child of root node. So it is also on level 1. So the maximum height of the tree is 1. Right? Now we'll run it again for more number of nodes. So for more number of nodes, I will say, suppose I want to enter 7 nodes. So these 7 nodes are 10, 5 will be the left child of 10. Then we'll have 2, which is the left child of 5. Then we'll have 15, which is the right child of 10. Uh, yes, and after 15, we have 20, which is right child of 15. So 20 will be the right child of 15. And then we enter one more value. I think there is some problem after this. Okay, so we'll run it again. Okay, so let us enter 5 nodes. Now 10 is the root, then we have 5, then we have 2 in the left subtree. Now in the right subtree we have 15, and come on, yeah, and then we have 20. So these are the values we entered. 5 values, 5 nodes. So 10 is the root node, 5 is the left child of 10, 2 is the left child of 5. Then on the right of 10 we have 15, and on the right of 15 we have 20. But now here we are not getting the display. So suppose this will be our output. So these are our nodes. See, these are our nodes. 7 nodes: 10, 5, 2, 15, 20, 18. And then we have this output here. This is the output for display function. This is display C. So 10, which is the root, is on level 0. 5 is on level 1. Then 2 is on level 2. 15 is on level 1. 20 is on level C. Level 2. 18 is on level 3. And 24 is on level 3. So these are the values. 10 was the root, that is why it is on level 0. 5 is the left child of 10, that is why it is on level 1. 2 is the left child of 5, so it is on level 2. 15 is the right child of root, so that is why 15 is on level 1. And then 20 is the right child of 15, so that is why 20 is on level 2. And 18 is the left child of 20, that is why its level is 3. And 24 is the right child of 20, that is why its level is 4. Okay, so these are the levels. Now what we'll do, we'll see the third, that is output of third function, which is height of binary searched. So this will be the height of binary searched. See, the node at the highest level is this 24 and 18. So their height is 3, right? The deepest node is having height 3. So the height of BST is also 3, right? So I hope you have understood this program. Now you can also implement this program. So try this program. Happy learning, happy programming. Thank you.